Good morning, students. We are discussing the lesson oscillation. So this lesson we are going to discuss about the linear harmonic oscillator, LHO. So in this topic we are going to learn about the horizontal oscillations of a spring mass system. Horizontal oscillations of a spring mass system. Consider one massless spring. Okay, consider one massless spring. It is a frictionless spring. Okay, so it is a massless spring. That spring constant, that is a spring constant is K. It will be attached to one end is fixed, and another one end is fixed with one mass. That mass is M. This whole setup, that spring and mass, this will be placed in one smooth surface, that is a frictionless surface. Okay, so consider one spring, that spring having spring constant K. Okay, then another one, this one end is fixed with one end is fixed, and another one end is attached with one mass M. So this setup is placed in the one smooth surface, that is a frictionless surface. Initially they are undisturbed. Okay, it is not it is a undisturbed, that it will be on equilibrium position. So that equilibrium position, so that distance is x naught. X naught is the equilibrium position. That mass is M. You can measure that. Okay, from this place to this place, that is the equilibrium position. So that distance is x naught. Okay, equilibrium position or mean position. So from that mean position, it will be moving back and forth. Suppose there is no force acting, it will be an equilibrium. So that distance is x naught. Now one force is acting, that is the restoring force, maybe any one side. Okay, so that place is x naught and this place is x1. Okay, so that a small force, elongated forces, that is the restoring forces applied, it will be elongated at the distance of x1. Okay, or suppose if you remove the restoring force, it will be back and forth. Okay, so it will be oscillating. So here, so there is the moving in a small distance x1, that is the displacement x1. If you apply if you applied any one disturbance, or if you applied any one force, okay, in any direction, it will be moving back and forth. Back and forth, it will be oscillating about their mean position, that is the x naught. Okay, so that distance is x1. Okay, do you understand? That distance is x1, or you can simply write that x. That force is directly proportional to x. When you are applying a large force, the displacement of that mass is larger. Okay, when you apply the small amount of force, that is when the displacement of mass of the bob is very small. Okay, now you can equate this equation. So f is equal to minus kx. So minus k is representing the force constant. Okay, minus k is representing force constant. That is always to be a negative. Why that is always to be a negative means that that force constant is always acting upon the opposite to the direction of applied force. Okay, or restoring force. That force constant is always opposite to the direction of restoring force. So only we can write this F is equal to minus Kx. Okay, you understand? Then next, according to Newton's second law. What is Newton's second law? F is equal to ma, or F is equal to m into dv by dt. Rate of change of velocity. Acceleration is defined as the rate of change of velocity. Okay, so m into dv by dt. Then F is equal to m into d by dt of, then velocity. How to define that velocity? That velocity is rate of change of displacement. That is dx by dt. Then F is equal to m into d squared x by dt squared. M into d squared x by dt squared. Okay, so this restoring force will be equal to m into d squared x by dt squared. That m is the mass and x is the displacement. You can apply this equation. This is the equation number 1. Okay, so you can apply it. Then m d squared x by dt squared is equal to minus kx. Okay, here d squared x by dt squared is equal to minus omega squared x. So there is the acceleration is equal to minus omega squared x. You already know that. Okay, so d squared x equal to d squared x by dt squared is equal to minus omega squared x. You can now apply this equation. M d squared x, you can apply minus omega squared x is equal to minus kx. So this minus and this minus cancel, and x, this x also cancel. So omega squared is equal to k by m. Then omega is equal to square root of k by m. Okay, omega is equal to square root of k by m. Then frequent time period. How to define time period? T is equal to 2 pi omega. The time period is T is equal to 2 pi omega. So this is the time period. Okay. Then T is equal to 2 pi divided by, you can apply this square root of k by m. Then T is equal to 2 pi square root of m divided by k. So the time period of that spring is T is equal to 2 pi square root of m by k. Next, you can calculate the frequency. Frequency is equal to, what is the formula? 2 pi nu or 2 pi omega. Okay, frequency is equal to, or frequency is equal to 1 by t. F is equal to 1 by t. Then F is equal to 1 by t. That is 1 by 2 pi square root of k divided by m. So here time period is equal to 2 pi square root of m by k, and frequency is equal to 1 by 2 pi square root of k by m. Here the time period does not depends upon the amplitude. Okay, do you understand? So this is the simple harmonic motion. The time period or frequency does not depends upon their amplitude. Okay, then next, so this is the differential equation. D squared x by dt squared is equal to minus omega squared x is the differential equation. So differential equation having some solution. So that solutions are x of t. X is the function of t. At x is the function of t. So only I can write this x of t is equal to a sine omega t plus pi. A sine omega t plus pi. Or another one form, x of t is equal to a cos omega t plus pi. X of t is equal to a cos omega t plus pi. So these two equations are a solution of this differential equation. Okay, do you understand, ma? Okay, thank you.